common is a soccer ball. Soccer ball will also be featured in my talk. Okay, big data, big discoveries, big fallacies. Let's start by answering the question, what is big data anyway? What does it mean? I'm sure all of you have heard it, it's probably too much. I'm going to give you a quick definition. Big data is the process of collecting large amounts of data and then actually doing something with it. So where is that data coming from? Let me try to revise this microphone. Where is that data coming from? It could be coming from computers, that's one of the most common things. It could be coming from sensors embedded in various places. It could be coming from people. And what does it mean to do something with that data? Well, we might use it to make decisions, we might use it to make predictions, we might have a hypothesis we want to confirm and we need data to do that, or we might just want to gain some insight from the data. Now, you've probably also heard the term data science, and none of these definitions are perfect, but I'm going to say that data science is the science of going from 1 to 2, of going from the collected data to some insight, some confirmation of hypothesis, something you're doing with the data. Somebody recently asked me the question, is big data a fad? And my answer to that is, well, 30 years ago, was computer programming a fad? People might have thought so at the time. I would argue that it wasn't at the time, and that's proven itself out. I would say that the ability to collect data is only going to increase over time. I don't see that slowing down. And the ability to analyze that data will only improve. So I don't see that anything is going to go away, and that's my argument that this is not a fad. Okay, so what am I going to do in this talk? I promised discoveries, fallacies, and so on. What I'm going to start is with a few success stories of big data, things I hope that you can relate to. Relatively quick, just go through some examples. I think you'll all be able to generate more examples for yourself from your everyday experience. I'm going to spend a reasonable amount of time on the pitfalls. It's going to get slightly technical, but I think most of you will probably be able to follow most of it. And then if there's time, I have one last slide that is just about some techniques and tools. And this is just sort of to demystify terminology. You can then use these at your next cocktail party. Okay, so here's my first big data success story, and this is traffic. So most of you probably use Google Maps or something similar. When you want to find out what's happening with the traffic, you pull it up and you see the red is where the traffic is stopped, yellow is where it's partially stopped, and green is where things are good. Everybody know where that data is coming from, how it's being collected? Being collected from your smartphones. So there are not sensors in those streets telling you how fast the cars are moving. When you use your phone, you have agreed to transmit your location, and there are enough cars going around transmitting their location on a second-by-second basis to determine how fast those cars are moving, and that's where that data is coming from. So here, oops. Oh, you told me not to press that button. Now what do I do? Okay. He said no matter what you do, don't press that button. Okay. On my clicker, that's going. Okay. Anyway, all right. Here we go. Anyway, this is an example where data is being collected. In this case, it's being collected but from everybody's smartphones. And it's a lot of data, and we're doing something with it, or people are doing something with it, which is to make these maps that are generally useful for people. All right, another example that you're probably very familiar with is recommendation systems. So Amazon will tell you what they think you ought to buy. Netflix will tell you what movies that you ought to be watching. How do they do this? They do this by collecting a huge amount of data. So they not only collect what everybody buys, they also collect what they don't buy, what they look at and don't buy, what they buy together, what movies they watch, how they rate the movies, what movies are rated together, and as much as possible, as much information about those people as they can get their hands on. Gender, age, where they live, and so forth. And all that is put together to some pretty sophisticated algorithms that tell you what they think you're going to like. You may not agree with them, but that's what they're doing. So again, collecting a lot of data about everybody's buying or watching patterns and about their personal information, and then doing something with it, which is recommendations. And by the way, you will, as you can imagine, advertising follows a generally similar pattern, which is slightly more distasteful. Okay, third example for any sports fans out there. So I'm not heavily familiar with sports, but I had a student in my freshman class who was very interested in sports data, and he uncovered the following. Apparently in basketball, all of the games are videoed, every detail of the games. And then they are computer analyzed to generate statistics. So in baseball, for example, you know their statistics is very straightforward, that people are just writing down, he hit the ball, he got to this base. But in basketball, it's a little more subtle. The computer analyzes the video. And in this one particular example, they found that this one player, Kobe Bryant, whoever he is, on the occasions that he took this one shot when his team had the ball, the pull-up jumper going to his left hand, on those occasions, the possession of their team converted to, on average, 0.1 points less than they got over all the times they had the ball. So if the opposing team could force Kobe Bryant to the pull-up jumper going to the left hand, then that brings down the expected score of that team. And apparently the 0.1 points over a single game over a whole season is very significant. And so this was something that was actually used. This cartoon here is a little bit related to that. Here's my soccer ball, it's not huge. But this cartoon says, remember the other team is counting on big data insights based on previous games, so kick the ball with your other foot. So this is another example, and this is happening all over sports. Like baseball, again, we know those statistics have been around for a long time. People know Moneyball. But in sports like basketball, it's generally video, hockey also, and it's going on all over the place. Collecting everything they can about the games and then doing something with it, which is trying to figure out their strategy for the next game. Okay, just a couple more examples. I picked this one partly because, well, two reasons. One is this example comes from right where we're standing, the Stanford Medical School, and the second because this project was around way before big data was popular. This is a project done by Russ Altman, a faculty member here, where he's been collecting over, I think it's been maybe almost a couple decades now, information about the relationship between human genetic variation and drug responses. And he's just collected this information and curated it and put it in a big database for other researchers to use. And I wanted to point this out also because in this case, and this is a pretty common one in science, he's not actually collecting the data and necessarily himself doing something with it. He's collecting the data, he's curating that data, and he's making it available for others. And by the way, curating data, it's a sort of catch-all term for making sure the data is clean and consistent and usable. And most people who embark on a big data project will find that they spend 90% of their time getting their data curated, cleaned up, and ready, and 10% of their time doing the actual analysis. Again, I taught a freshman seminar where they all did projects, and they were just floored by that ratio there. Another example, sort of along the same lines, is ocean health. So at this point, there are about 44,000 some sensors out there in the ocean that are generating all kinds of measurements. They're physical about the waves, they're chemical, they're biological, and they're all being assembled, put together, and made available for scientists to use. So another example of gathering data, curating data, but then putting it out there. Okay. So that's going to be the end of my success stories, but again, I don't think any of you will have any difficulty thinking of your own. So now I'm going to get into the pitfalls, and I'm going to zoom through quite a few of them. Correlation, causation, underfitting, overfitting, sampling bias, privacy, and then I have a couple that don't fall in a category, and they happen to both pick on Google a little bit. I hope I'll have time to get to them. I know I'm moving fast, but I'll also be available afterwards. Okay. Correlation and causation are two things that are often mixed up. People frequently like to say correlation does not imply causation. And so people often mix those two things up. Let me try to explain them for you. Correlation and causation are talking about relationships between data values. So correlation says we've got two values that tend to track each other. They go up together, they go down together. Causation says one value influences another value. And I'm just going to give you some examples. So for correlation, height and shoe size are correlated. People who are taller tend to have bigger feet, smaller feet. Grades and test scores tend to be correlated. People with high grades often have high test scores and vice versa. Okay? Causation is an example where one thing actually directly influences the other. For example, education level may be used to set someone's salary. There's a causation there. Temperature, if it's warmer, people might buy ice cream. The important thing to know is that neither one of these implies the other. So in correlation, the two examples I gave, it's not that the height is causing your shoes to be bigger or the grades are causing your test scores to be higher, okay? And even in causation, although education level may influence salary, you can have your salary go up without having a higher education level, or there might be a spike in ice cream sales even on a cold day. So there's not correlation there, there's causation. Here's another favorite cartoon of mine. This one is, it's really old actually, and this child is flying on the airplane with his mother and says, I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy. So this is an example actually of causation, but he's got the causation in the wrong direction there. A little bit more about causation and correlation. Frequently, but not always, when two things are correlated, it's because there's this hidden thing called the confounding variable that has causation to both of the correlated values. So if you might have a situation where A and B are correlated because there's a hidden C that implies both A and B. And I'll just give you an example. We might have the fact that the homeless population and the crime rate in an area are correlated. When homeless population and crime rate go up together, they go down together. It's not because the homeless people are committing crimes, and it's not because crime is causing people to be homeless. So there's no direct causation, but there is a hidden causation of this confounding variable in this case, or there might be, which is unemployment, which itself causes population, the homeless and the crime rate. And when unemployment goes up, those other two things go up together. Now there's also cases where things appear correlated, but there is no causation, and in fact they don't cause each other at all. And that's really the problem that can come up in data analysis. And there's a few entertaining ones I'm going to give you. For example, let me just explain this graph, and I'm going to show you 4 graphs that look kind of similar. We've got a timeline here from 2000 to 2009, and the red line is plotting the total revenue generated by arcades, okay, over that period, and there's the scale. The black line is computer science doctorates awarded in the US, and that's the scale over here. And we can see remarkably those two things track very nicely. I don't think there's any causation involved there at all, not even a hidden confounding variable, I'm pretty sure. Similar behavior. Drivers killed by collision with a railway train and US crude oil imports from Norway. Closely correlated. I could go on and on. Letters in the winning word of the Scripps National Spelling Bee is correlated very closely with people killed by spiders. And the age of Miss America, remarkably correlated with people who were murdered by steam, hot vapor, or hot objects. Okay, so these are all very entertaining. Actually, these all come from a website or a service that has gathered thousands, maybe tens of thousands of these graphs, of these trends. And you can go on there and you can just pick one and say, tell me what's correlated with this one. And because there's so many of them, it's pretty easy to find pairs of things that have nothing to do with each other that show similar curves. So it's kind of fun. You can find this all over the web now. People have had a great time playing with that website. Okay, done with causation and correlation. Now let's talk about underfitting and overfitting, which is another mistake that people can make in data analysis. Underfitting is drawing conclusions from data that are effectively too simplistic. And my explanation is a little simplistic too, but I think you'll get the idea. Okay, so as background, I'm going to briefly explain to you the idea of regression. Regression basically says, I have some data points, and I'm going to try to extract a trend from those data points. That's the high-level idea of what regression is about. So here's an example where we have a graph of people's heights and weights. I couldn't figure out what this scale is, but anyway, it's a graph of people. This is a set of people in the population, and each data point represents someone's height and weight. For example, this is 60 and 80, okay? And when we gather all this data, and then there's an algorithm for drawing a line that's called a linear regression through those data points. And what you use that line for is to predict the height or weight of someone else. So after you've taken the sample of the data, you draw the line. If someone comes along with, height of 53, then you would go right up to this point in the line and say, I'm going to predict that's their weight. Okay? That's what linear regression does. Another example here is we have high school GPA and we have university GPA, and you can see there's some trend there. You draw the line, and that would tell you, okay, if someone comes along with a 3.12 GPA, I'm just going to go up to the line and predict. Or you can go the other way too. You can predict what their high school GPA was from their university or their height from their weight. Okay, now there is an algorithm to draw the best line for the points. So you get a set of points, and there is a way to draw the line. Basically, it adds up the, now what do I do? Not bad. Okay. I'm giving away my thing here. Okay, there is an algorithm for figuring out how to draw the line. You basically try to minimize the sum of the distance from the points to the line. Actually, the sum they're squares, but that doesn't matter that much. Now, I'm going to show you why this doesn't always work. It really only works when you have a nice trend. And underfitting is when you draw a line, but you're really not capturing, the real shape of the data. So I'm going to point out that there are 4 different sets of points that look completely different that all have identical lines. And here they are. So the algorithm to draw the regression line for each of these, this is the best line. It's absolutely identical for each of these. I think you would agree the points themselves are not similar at all. Here we ought to be catching that vertical thing. Here we ought to have that curve, and so on. So the process of underfitting is being too simplistic here. The line is too simplistic. This one looks okay, but for the rest, too simplistic to capture the meaning of the data. Okay, where underfitting is too simplistic, overfitting is too specific. And again, I'm just going to show you example. Now, let's say we're not always going to draw lines. We're willing to draw curves to capture the trend in our data. So here's an example that one would say is classic overfitting. We have these points, and we draw a curve that tries to capture every little change in those points. That's overfitting. The same data, by the way, would be underfit with a line because it's missing that there's a shape here. What would be just right would be to get a curve something like this in this particular case, doing regression. Here's another example of overfitting, and this is another comic. I don't know how well you can read this, and you're certainly not expected to read all of it. This is using regression to try to decide who wins presidential elections, which is a very timely example. So here at the beginning, well, the regression says the incumbent never wins. But then there's somebody who actually violated that. Then they say, okay, well, no congressman has ever become president. And so with everything that happens, the regression takes that very specific thing and says that's the algorithm for deciding who's going to win. And it's kind of fun. I mean, there are fun examples like as goes Mississippi, so goes the nation, and so on. Okay, so that's another example of overfitting that's not an actual graph. Okay, next, pitfall, sampling bias. So far I've been talking about pitfalls in doing something with the data. We've collected the data, and now we're going to do something, and we make mistakes in the doing something. Causation, correlation, underfitting, overfitting. Now let's talk about mistakes that can be made in the actual collection of the data. And I'm going to use another presidential election example. I'm going to wind back to 1936, Landon versus Roosevelt. How many people in the room know this story? 1. Okay, good. You'll all learn something here. Okay, so it's 1936. These are the people who are being running off for president. And at the time, the Reader's Digest, a magazine, was known for very accurate predictions of presidential races and other things. In 1932, they had a 1% error in their prediction of the presidential election. So in 1936, they surveyed a whopping 10% of the population. 25% of those returned the survey. They predicted from that sample that Landon would win in a landslide. Well, Roosevelt won. So, in fact, it was a really bad prediction. They were 19% off, which is, at that time, was the worst error in any major opinion. And the problem was that their sampling method was not good. It was biased. There were 2 kinds. There was this, what's known as survey sample bias and non-response bias. And the survey sample bias is that at the time, it was the Depression, and they sent the surveys to their people who are subscribing to the magazine. They used phone books to send the survey. And they were very much biased towards the wealthier segment of the population just because of who they sent the survey to. Non-response bias has to do with who returns the survey. 25% returned the survey, but again, that was skewed towards the wealthier 25% who actually sent it in, and therefore they got a wrong result. And by the way, another example is experiments that are done through people's mobile phones, even when they're agreeing to do it. People who have iPhones are much wealthier in general than people who have Androids. So when there's ever a survey that's done on iPhones, for example, that will get a very skewed percent sample of the population. So very similar type of thing. Now everybody's favorite topic is privacy. I'm only going to talk about this topic very briefly. Some of you might have had a little thinking about that when you realized your phone was being tracked to make Google Maps. You opted into that probably, or didn't opt out anyway. So there have been many cases of improper covert collection of individual data, and we all know about Snowden and so on. But there's a lot of collection going on that you might not be aware of. Data can kind of bleed legally through surprising channels. And the example I'm going to give here is Angry Birds. Anybody who wants to play Angry Birds, I think it's sort of out of fashion now, but at the time, anybody who played Angry Birds agreed to a bunch of data being transmitted because they are signing up for the game. And most people don't read it. You sign up for an app, it says, screen after screen, okay, fine. And one thing is that you agree to, when you play Angry Birds, to transmit all the information about the Wi-Fi networks that your phone can see, anytime, okay? And why do they want that information? Well, what they really are trying to get is location information. So even if you say you don't want to be tracked on your phone using the location, using the GPS, it has been shown that by looking at what Wi-Fi networks you can see at a given time, your position can be put almost as accurate as a GPS position. That experiments have shown that to be the case. So beware, your private data is being transmitted, not always in ways that you expect. Okay, two more pitfall examples, and again I said, unfortunately I'm picking on Google twice here, but that's probably because Google is doing a lot of the big data things around here. One is about Google Flu Trends, and the other is about Google Translate. So, I don't know how many of you noticed the news around 2006 or 7 that Google had shown that they could predict the flu passing across the United States more accurately than the Center for Disease Control. And they were doing it by looking at what people were searching for. They were searching for flu symptoms. They knew where they were searching from. So that was pretty impressive until it failed. So the third year of Google Flu Trends, they were way off. They were off by like 50%. It was amazing. It turned out that year maybe there was something going on with the flu shot, or maybe people were Googling flu trends, but they weren't Googling the flu stuff because they had the flu. And so that also spawned the phrase, which I like, big data hubris, where people were, overconfident that simple things like web search terms were going to tell you the truth about big stuff. Another example is Google Translate. So actually Google Translate is an amazing example of take a lot of data and do something with it. The way Google Translate works, and I'm talking about translating from one language to another, many of you have probably used it, and it's not bad. The way it actually works is it's learned how to translate automatically. It has been going around the web, the computers have, looking at cases where there are things in two languages, comparing them, mapping them, and learning the mappings between pairs of languages. And that's how it has learned to do translation. There's people that are tuning it, but nobody's sitting there and teaching it how to translate. It's doing it from examples. The problem comes, and this is a real problem, when the examples that it's using were actually translated by it. And it doesn't know that. And so somebody put two things up there because they use Google Translate, and if there's a mistake, it just continuously reinforces itself. So that's another example of pitfalls. Okay, enough negativity. I do think the discoveries outweigh the fallacies. I think the balance between those will only improve. Big data is not a fad, is my main message here. Last 1 minute, quick careening through what are like 5 or 10 different courses at Stanford in 30 seconds. Data management systems. Data management systems have been around for decades. Oracle, relational database management systems, 40, 50 years, huge industry, will never go away. It's about convenient management of large amounts of data. Banks use this, the registrar uses it, and then you ask well-formed questions. Get me all the dorms that sophomores are living in. Find all people whose bank account is getting too low. That's what those are about. Relational SQL databases, now there's things called NoSQL systems, but they're not opposites at all. That's what they do. Data mining is fundamentally different. Data mining is about looking for patterns in data. So instead of asking a specific question, you say, here's all my data, find some patterns. Patterns, things that are frequently bought together would be a pattern. People who buy this, buy that. That's the type of thing data mining does. And lastly, machine learning is the process of using a set of data to create models about how things are or to predict the future. So regression that I showed you was an example where we're using one data set and trying to generalize. And that's what people mean by machine learning. Regression clustering is another machine learning technique classification. Okay, so 5 courses in 30 seconds, and I'm done. Thank you.